Now we're going to look at how theory-driven processing aids in our speech perception. Theory-driven processing is really important for speech perception, partially because speech perception is just so challenging for our brains. Speech sounds are made so fast, they're coming at us very, very rapidly. Because an individual making them has to co-articulate, it means that the different speech sounds are not always consistently the same, leading us to have to categorize the sounds. A further complication is something called word segmentation. And basically, it means that we don't really insert a silence or a gap between words. So if we read the sentence, where are the silences between words? We can see here that there really aren't any clear gaps. There aren't any silences when people say the sentence. Very brief one maybe here, but not total silence, huh? And that means that we have to figure out where one word starts and another word ends. What sounds belong to one word and what sounds belong to another word. So here, where the individual says, where are is one continuous block of sound. How do we separate that out into two distinct words? We have to use our existing knowledge of the language. And so if you've ever tried to learn a foreign language, this may have been something that you really found challenging when listening to native speakers. Your instructor may have spoken very clearly like this, but a native speaker would not. And that means that when you listen to a native speaker, you're not going to have those artificial gaps between sentences, making it very challenging to identify distinct words until you have sufficient familiarity with the language. Here's an example. Here's an English sentence that should be easy to parse out into words.
Though it's very cold, children are still playing outside.
Here's another.
Lions like cherry, lemon, and lime popsicles.
So even though it's a silly sentence about lions liking different types of popsicles, we still probably understood where one word started and another word ended. Now let's try Chinese.
山羊在我的萝卜地里，而且我赶不走它们。
I'll play it again, and this time, just try and figure out how many words there might be. This will be tough if you're not a Chinese speaker.
山羊在我的萝卜地里，而且我赶不走它们。
I don't know. I'm guessing 7 words. Hard to say. 13 words. Let's do Arabic.
عندما أسافر للخارج دائما آخذ معي 3 صناديق من الكعك المصري.
Wow. 14 words? 11 words. So you can see that parsing sounds into words is really, really difficult in a foreign language because we don't pause between words. That is what's called the segmentation problem. Another example of theory-driven processing is what happens in something called the phonemic restoration effect. This is when a missing sound, a missing phoneme, is sort of restored for us by our brain. So if a cough or some other source of broad spectrum white noise replaces a sound in a meaningful sentence, people hear the missing phoneme. So here is an example.
The state governors met with their respective legislatures convening in the capital city. The state governors met with their respective legislatures convening in the capital city.
So in the word legislatures, the S is covered up and it's actually missing, it's absent. And instead, there's a cough. But you probably hear an S in that word. I'll play it again.
The state governors met with their respective legislatures convening in the capital city.
There really is no S. And if the cough is removed, then people just hear a gap. They won't hear the missing S. But if there's some sound source in there, it's as if our brain knows, okay, how many words could it possibly be? And the fact that there's a sound there, but it's not quite right, means that the brain can sort of say, you know what, there's a sound here, it's not quite right. I'm going to assume that's some sort of mistake, and it will insert the missing phoneme. So that's theory-driven processing because it only works for a familiar word and in a meaningful sentence or phrase. But bottom-up or data-driven processing is also involved. In fact, that restoration is better if the masking noise, like a cough, is more similar to a missing sound versus, say, if it was a click or something like that, that would be really different than the S. And here's another example. If the sentence was, British viewers flock to the opening performance of Doctor Who, here they will hear the N sound in night. If the sentence was, it was found that the eel was on the axle, people will hear the sound for wheel. But here, cough with eel will be heard differently if the sentence was, it was found that the eel was on the orange. Now people will hear a P. So the context, the meaning of the sentence, helps determine what sound we hear. And that's an example of theory-driven processing. We're using our knowledge and our expectations of what that sound should be to help fill it in. And there's evidence showing that the prefrontal cortex can help provide a context for sounds being processed by the auditory cortex.